In this video, you will learn to make your autonomous car automatically stay in a lane by using infrared sensors to detect the lane lines. You can also use the sensors to program other behaviors, like automatically stopping at a crosswalk. Before we can do that, we are going to revisit the infrared sensor. We covered these sensors in detail in a previous video, but as a quick reminder, they work by emitting infrared light and measuring when that light is reflected back to the sensor. This lets them serve to detect objects that are a short distance in front of the sensor, and they can also work to differentiate between light and dark surfaces, depending on how much infrared light those surfaces reflect. So for example, here I have the Arduino program to light up the green LED when the sensor that I am holding detects a light surface. However, I am doing that with the digital read command, and the result is that I have something that is very sensitive to the distance of the sensor from the surface. You see that even though this black surface looks dark to the human eye seeing visible light, it does actually reflect enough infrared light to activate the sensor and light up the LED sometimes. So that would be a problem if I had my Arduino autonomous car driving around and I wanted to detect lane markers, because sometimes I would get a false reading when my sensor isn't over the line, it's just over the black road surface. We can help alleviate this problem by using the analog read command instead of digital read. Remember that an analog signal can take on any value within a range instead of a digital signal, which is only ever high or low. Here I have a second sensor hooked up to the Arduino, and it is programmed to turn on the red LED when it sees enough reflected infrared light, but I am using the analog read command and comparing the analog value to a threshold that I set in the code. And you see that the basic behavior is still the same, but this way it is much less sensitive to changes in distance, and I am not getting false positive readings when I am over the black paper. I can move the sensor up and down, and the red LED does not turn on. This approach gives you more flexibility when mounting the sensor on a vehicle, especially if you are driving around on a surface that is not perfectly flat and the sensor might wobble up and down a little bit. You're going to need to have some tolerance for that changing distance. You can see that if I take the sensor that is programmed with digital read, then again I am getting a lot of false positive readings when I'm over the black surface depending on the distance. That would cause a problem when your car thinks it has detected a line, but the sensor is actually over the normal road surface. So now we're going to go over the circuit and code to switch to using analog read with this sensor. This is the circuit that you built previously. The sensor has 4 wires, one of which is connected to a 220 ohm resistor, which is connected to 5 volts. 2 of them are connected to ground, and then one is connected to one of the Arduino's digital pins. You can go back to the full video about the infrared sensor for all the details, but as a quick reminder, if you place the sensor with the pins facing you, so the notch is in the bottom right corner, then the pins are numbered 1, 2, 3, 4, going counterclockwise from the top left. If you attach blue, black, green, and red jumper wires to those pins respectively, then you can follow those diagrams in the video just using the wire colors and not having to go back and figure out which pin is which. In this diagram, I have connected 2 sensors to the Arduino. One is connected to one of the digital pins, just like in the previous diagram. However, I have the other one connected to one of the Arduino's analog input pins. The only other part I have added here is a 10 kilo ohm pull-up resistor, which is also connected from that output pin of the sensor to 5 volts. We need that to make it work with the analog input. That works due to something called Ohm's law, which we're not going to cover in this video, but the very short explanation is that as the amount of current flowing through this resistor changes, the voltage drop across it changes. So the voltage at this point in the breadboard will change, and that is measured by the analog input. Now, remember that Tinkercad Circuits does not have this particular infrared sensor in its parts library, so this is just a static diagram that you can follow to build the circuit on your breadboard, but it is not a simulation that I can run to demonstrate in the video. So, pause the video here and assemble this circuit on your breadboard. Note that if you have already assembled your vehicle and have other parts on your circuit like the H-bridge or the ultrasonic sensor, then you may need to put these wires for the sensors in different breadboard rows so you don't have to move the rest of your circuit. That is okay. You do not need to follow the connections exactly as I have them in this diagram. You just have to remember how a breadboard works, which we covered in an earlier video in this series, and you can put the connections in different places. Note that we also have 2 LEDs that we are going to use as outputs to indicate when each sensor is activated. So for now, go ahead and build this circuit where we are only going to connect one of the sensors to the analog input, and we are going to leave the other sensor connected to a digital input so we can compare their behavior. Let's switch over to the Arduino IDE and take a look at how this works and compare the digital and analog inputs. So, at the beginning of the program, we declare constants for the pins we're using. We have 2 sensor pins and 2 LED pins. Note that one of these sensor pins is an analog pin, so that is pin A0 instead of just a number like we have for the digital pins. Then we have 2 variables for the sensor readings. We are declaring both of them as integers, but the one for sensor 1 will only be digital, so it will only ever have 2 different values. The value for sensor 2 will be analog, so it will go between 0 and 1023. Finally, we have one new variable, the threshold we are going to define to compare to the analog reading for sensor 2. Right now, I have that set to a value of 200, but you can change that based on the lighting conditions where you are working and the reflectivity of the surfaces you are using. In our setup function, we set the pin for sensor 1 as an input with the internal pull-up resistor enabled, so this simplifies the circuit a bit and we don't need an external pull-up resistor. And we set the 2 LED pins as outputs. Note that you do not need to use the pin mode command with an analog input pin. Then, in our loop function, we have 2 different read commands. We are using digital read for sensor 1 and analog read for sensor 2. Then, we have 2 different if-else statements to control the 2 LEDs. Sensor 1 is digital, so we are just using the if statement to check if that sensor value is high or low. If the value is high, that means it's not detecting infrared light or the sensor sees a dark surface, so we're going to turn the LED off. Else, the value is low, that means we do see infrared light, the sensor sees a light surface, and we're going to turn the LED on. The if statement for sensor 2 is a little different. Instead of checking if sensor 2 value is equal to high or low, we are checking if it is greater than the threshold variable that we set earlier. Remember, sensor 2 with analog read can take on a value between 0 and 1023. This threshold value we set to a value of 200. So if this value is greater than 200, that means we are getting a higher analog value, which corresponds to less reflected light or a darker surface. So again, we're then going to turn the LED off. Else, if sensor 2 is less than this value, we are reflecting more light, we're seeing a light surface, and we're going to turn the LED on. So, go ahead, pause the video here, enter this example code, upload it, and then test out your 2 different sensors. After uploading the code, you should see what I demonstrated earlier in the video. If you take the sensor that is connected to the digital input pin, which is controlling the green LED here, if you hold it at exactly the right distance, it will work to differentiate between light and dark surfaces. But if you move it around, for example, if I move it a little farther away, then the LED is still lighting up even when I'm over the dark surface. If I take the sensor connected to the analog pin, then it works much better. The LED does not turn on when I'm over the dark surface, even if I move the sensor up and down, and it does turn on when I go over either one of the light surfaces. Now, if you try it and you are still having trouble, for example, if your sensor is not turning on when you're over a light surface, or it is turning on when you're over a dark surface, then you can try adjusting the threshold value in your code. Rather than just guessing a value for the threshold, you can use the serial print command to print the analog reading out to the serial monitor as you test your sensor over different surfaces. You do that by adding the serial begin command to the setup function to initialize serial communication, and the serial.println command to your loop function, which will print out each analog reading on a new line. Then, when you open the serial monitor, you will see the analog reading print out continuously as you move your sensor around. Right now, I am holding my sensor above the black surface. We see that even if I move the sensor up and down a little bit, the reading stays above 300. If I move the sensor over to, for example, the yellow line, the reading drops dramatically to under 100. And again, even if I move it up and down a little bit, it stays below 200. So, a threshold value of maybe 200 or 250 works well in this case to differentiate between the 2 surfaces. The materials you're using for your track might reflect different amounts of infrared light than mine. So, for example, if you were getting readings of 7 or 800 for your dark road surface and 3 or 400 for the lighter lines, then a threshold value of 5 or 600 would work better. So, if needed, pause the video here and calibrate your sensor. Add the serial print commands to print out the analog value, and then look at the value as you hold your sensor over different surfaces. Make sure the sensor is at least a few millimeters from the surface and not touching or scraping the surface. Then, if needed, change the threshold value so you can more easily differentiate between the different colors on your road. After you get that threshold value working, you will want to switch your circuit and code around so both sensors are connected to an analog input. So pause the video here and see if you can figure that out yourself, and then I will show an example circuit diagram and code. Here is the original breadboard diagram where we have one sensor connected to an analog input and one sensor connected to a digital input. To switch this one to analog, we need to move the wire over to one of the analog input pins, but you also need to remember that you have to add this 10 kilo ohm pull-up resistor to 5 volts. Now, depending on what order you have been doing these lessons in, if you did this one early or have been taking circuits apart in between lessons, then you might have a blank breadboard where you can just connect these two sensors. However, if you have been following everything in order and you are building an autonomous vehicle, then you will already have a breadboard with an H-bridge and 2 motors connected and possibly the ultrasonic sensor. All of these parts take up a lot of breadboard real estate, so you won't be able to connect everything exactly where I have it shown in this diagram. You will need to utilize the blank space on your breadboard to connect the sensors. So for example, in this diagram, I have my 2 sensors connected where I had some blank space on the breadboard. Remember that you do not have to build your circuit exactly like I have it shown in this video and put every wire in exactly the same holes I have here. As long as you remember how a breadboard works, which we covered earlier in this video series, you can rearrange things if you want and put all the parts where you think it makes the most sense and is the easiest for you to keep track of everything. So once you have your sensors connected to those 2 analog inputs, and again, that is whether you already have the H-bridge on your circuit or if you are just working with the sensors and LEDs for now, let's switch over and look at the code to read both sensors with the analog inputs. This program is very similar to what we had before. We have just changed the code for the digital sensor to match that for the analog sensor. So for example, we're going to use analog input pin A1. We do not need to declare that analog pin as an input in the setup function. Then we are going to use the analog read function to read that pin. And finally, in the if statement, instead of checking if this value is equal to high or low, we are also going to check if it is greater than the threshold. Now, if for some reason you wanted 2 different thresholds for your different sensors, you could do that. Here I am using the same threshold value for both sensors, but remember in the video we saw earlier, I had one yellow line and one white line. So for example, if you are getting slightly different readings from 2 different color lines and you want to have different threshold variables, you could do that in your code instead. Now that you have 2 sensors working with analog read, it's time for your next challenge. You'll need to mount the sensors to the chassis of your vehicle. You can do this using craft materials like tape and popsicle sticks or cardboard. Make sure the sensors are downward facing and at least a few millimeters from the ground. The exact distance you pick might depend on the calibration you did earlier. Then, program your Arduino so the motors react to the sensors. How you define the behavior will depend on the environment you're using to test your car. For example, here you see an oval-shaped track with solid lane lines. If neither sensor sees one of the lines, then the car knows it should drive straight. If one of the sensors sees a line, then the car knows it is going off the road and needs to turn in the opposite direction. Here you can see, since the track only curves in one direction, the right-hand sensor sees the white line and the car knows to turn left. If the car overcorrects and turns too far left, then the left sensor will see the yellow line and the car will know to turn right. So at this point, to continue, you will need an assembled car with motors connected to the H-bridge and functions programmed to make it steer. If you haven't done that already, it's covered in previous videos in this series. Then, modify your program so the motors react to the infrared sensor readings to steer autonomously. If you need some help with that, here are some hints. I have two programs open side by side here. The one we just wrote to read the two infrared sensors using the analog input pins, and one that we wrote in a previous video for automatic braking, to make the vehicle automatically stop if an ultrasonic sensor detects an obstacle in front of it. Now, you can ignore the ultrasonic sensor if you want. You could even unplug it from your circuit if that makes things too messy and we can just focus on the infrared sensors. What we care about in this program is the code to control the motors. So again, this is covered in much more detail in previous videos in this series, but we have a bunch of different pins that are used to control the speed and direction of each motor, and then we have a bunch of functions that we have written for different behaviors like driving forward or turning. Having this code in functions is convenient because inside your main loop, you can just keep things neater with a single line to call those functions instead of having tons and tons of analog and digital write commands inside your loop function. In your loop function, you can make decisions based on sensor readings using if statements. For example, here we have a value in centimeters, or the distance of an obstacle in front of the ultrasonic sensor. We compare that to a threshold variable that we set. If the obstacle is less than that threshold, we stop driving. Otherwise, or else, we drive forward. So we can move over our code to take the analog readings for the infrared sensors. I'm going to copy that and paste it over here into this program. And I didn't do it, but I would also need to declare these variables up at the top of the program. If you don't declare a variable and then you try to use it, you will get an error message. And I can then write a new if statement using these values to determine my vehicle's behavior. However, the difference is that now I have two sensor readings instead of one. So we need to learn a little more about how to use the conditions in if statements to account for both readings. So the way to check multiple conditions in an if statement is to use something called a Boolean operator, and I will explain what this symbol means in a second. So reading it out in plain English, this statement is saying if sensor 1 is greater than threshold, and sensor 2 is greater than threshold. So this double ampersand here stands for and this entire statement will be considered true only if this statement in parentheses is true and this statement in parentheses is true. So both of these individual conditions must be met for the entire condition to be considered true and then for this code to happen. In this case, remember from our sensor program, if the sensor reading is greater than the threshold, then that means we're actually seeing a darker surface and less light is reflected. So that would mean both sensors are just seeing the road surface and not seeing a line. So this is asking, what should the car do if neither sensor sees a line? This is where you would fill in your code to call your appropriate driving function. Now, with a single sensor, there are only two possible combinations when comparing the sensor reading to a threshold. It could be either greater than or less than the threshold. But when you are looking at two sensor values together, that gives four possible combinations. You could have both readings greater than the threshold, both readings less than the threshold, the left sensor greater than the threshold while the right sensor is lower than the threshold, and vice versa, giving four combinations. So a single if-else statement isn't enough to check all four of those possible combinations. To do that, you need to use an if statement that has additional conditions using else if. So you can add as many else if statements as you want to your if statement to check additional conditions. And then finally, the last else statement will only happen if none of the previous conditions have been met. With those additional hints, see if you can pause the video here and fill in the conditions and actions based on what I have written in the comments. For example, what should the car do if only the left sensor sees a line? There are a couple things to keep in mind when doing this. For now, I have just deleted the if statement that was making the car react to the ultrasonic sensor, so it does not hurt to leave your ultrasonic sensor connected. It will keep taking readings, but the vehicle will not react to it. You also need to be careful when merging programs to look out for conflicting variable names. So I was already using the threshold variable name in this program for the ultrasonic sensor distance. I was also using a variable called threshold over here for my analog infrared light sensor readings. So I would need to make up two different variable names if I'm going to be using them both in the same program. Also, make sure that you declare all the variables that you are going to need. Right now, I am using these sensor 1 and sensor 1 pins variables down here, but I never declared those up top, so if I try to compile or upload my code, it will give me a bunch of error messages that says sensor 1 was not declared. So make sure you declare any variables that you're going to use when copying code over from your previous program. So again, pause the video here, see if you can fill in the conditions and actions for each one of these situations. Here is one example of how you could do that. So I have all of my conditions filled in. For the first one, if neither sensor sees a line, meaning both sensor readings are above the threshold, I'm just going to drive forward. If only the left sensor sees a line, so if my sensor 1 reading is less than the threshold, then I'm going to turn right. If only the right sensor sees a line, so the sensor 2 reading is less than the threshold, then I'm going to turn left. And finally, if both sensors see a line, I'm going to stop for 1 second. Now, note that I have set the delay value to 0 for all of these. Remember, in a previous video, we talked about how having a delay time inside these functions can prevent the vehicle from reacting quickly to changes in sensor input, so you generally do not want a long delay here. And I'm also doing everything full speed, so I have all my speed values set to 255, which could result in very jerky motion. So this is one simple solution, but it is not necessarily the best solution. You will need to test your vehicle on your track and tune these parameters to get the best performance. So now it's time to test. If your car is going too fast, it might overshoot the lines completely. If it turns too fast, it might overcorrect and zigzag back and forth. But if you set your motor speed too low, they might not have enough power, and your car could more easily get stuck. It's up to you to find the best parameters for your car and your track.